Okay, let's have a look at the problems for section 13. So the first one. So we've got a subset of X, and that for each element of this subset, there's an open set U containing X such that U is contained in A. I want to show that A is open in X. Okay, so for each X in A, we have that there is an open U. So let's call it U sub X just to make life easier for it. And we've got that X is contained in UX, and that's contained in A. Well, A is just the union of its points. And if we do this, then since each UX is in A, the union of them is going to be in A. But this is just a collection of open sets, and the arbitrary union of open sets is open. So this is open. Okay, so that was pretty straightforward. Okay, let's look at problem number 3 then. So remember, TC is the topology given by subsets whose complement is countable. So X itself is in this topology because X minus X is the empty set, and that's definitely countable. And the empty set is in this because X minus the empty set is X, and that was the one exception to things that could be countable that would be in this topology. And so what we're going to do now is show that arbitrary unions and finite intersections. Okay, so if we have some indexed family of non-empty elements of TC, then X minus the union of these things by De Morgan's law is equal to the intersection of X minus U alpha. So each one of these things is countable, and the arbitrary intersection of countable sets is countable. So therefore, the union is in TC. And then let's have a look at finite intersection. So this is a finite family of non-empty elements of TC. X minus the intersection of these guys is equal to the union of these complements. So since each one of these is countable, finite union of countable sets is countable. So therefore UI is in there. Note that T infinity is not topology. So remember, these are the ones such the complement is infinite or empty or all of X. For sure, X and the empty set are in T infinity. Well, let's consider R. Then singletons are going to be in T infinity, right? Because their complement is all points except that one point. But if a topology has all the singletons, then it has to be the discrete topology. And this is not equal to the discrete topology. For example, if we look at R minus a point, its complement is just the point. It's finite. It's not in T infinity, but it is a valid subset. So that doesn't work. So question 4. Is the intersection of a family of topologies a topology? Yes, it is, right? We just go through the various things. The empty set is in all topologies, so therefore it's in the intersection. The whole set is in every topology, so therefore it's in its intersection. So that's point one. Point two, we have to have arbitrary unions. Well, if we've got a collection of sets which is in every topology, then their intersection is going to be in every topology. And so that is going to be in that intersection topology. And the same with unions. If we have a collection of sets from that intersection, so when we take the union, since it's a topology and the topologies is closed by arbitrary unions, the arbitrary union is going to be in each topology. So therefore, it's going to be in the intersection. Now, what about the union of the topologies? Is that a topology? And the answer is no. And the simplest answer example I could come up with is take the upper limit and lower limit topologies on R. Right? So, for example, this guy is going to be in the lower limit topology. It's open in that. This guy is is in the upper limit topology. And if we have a look at the intersection of those two, that's going to equal 0, 1, the closed interval. We want that to be open for the union to be a topology, but this is not an open set in the lower limit topology, and it's not an open set in the lower limit topology. So it doesn't work. B. We have a family of topologies, so show that there is a unique smallest topology on X containing all the collections, and a unique largest topology contained in all of them. Well, the unique largest one is just going to be the intersection of those topologies. And the smallest topology containing all of them, well, you've got to take the union of them. Well, we know from part A that that doesn't have to be a topology, so we just then see what that generates. So use that as a sub-basis and take finite intersections and arbitrary unions and see what you get. And it's pretty straightforward to show that that works. Let's do it. Let's do part C. So what's the small topology containing T1 and T2? Well, it has to contain 0x, singleton A, doubleton AB, and then from 2. Okay, well, anything else that has to generate? Yes, it has to have the intersection of these two guys, so we need the singleton B. And you can satisfy yourself quite easily that that is a topology. And what is the largest topology contained in T1 and T2? If we look at the intersection, it's this guy. And that does that. And finally, problem number 8. Show that the countable collection of rational open intervals generates the standard topology on R. Well, using lemma 13.2, we want to show that for each open U in R and X in U, there is a B from this collection such that X is in B contained within U. And that's pretty straightforward. So we just have to show it for basis elements of the standard topology. So given any interval so let's say we're given some interval CD, which is containing U. So that's some arbitrary open interval. So C and D could be irrational, for example. And X is an element of this open interval. So we have C less than X, which is less than D. Well, by the density of the rationals in the reals, we have there exists an A in between C and X, and there exists a B between X and D. And so then we see that that works, right? So we've got AB contained within our CD, and X is in there. And so by 13.2, we see that this countable collection generates the same standard topology. What about part B? So now we want to show that those topologies are different. So we've got the lower limit topology, and then we've got the topology generated by the lower limits, where now the intervals are rational. So basically what we've got to show is that there exists an open set in one topology which is not open in another. So my example was the interval, the lower interval pi to 4. Okay, so this is an open set in the lower limit topology. Why is that not an open set in the topology generated by C? Well, pi is an element of that. So by 13.2, what we've got to do is we've got to show that there is some AB such that pi is in it, and that this is contained within this open set here. Okay, but A is rational, right? So that means A has to be lower than pi. Okay, but if we've got a number which is less than pi, it can't be contained within this this lower half open interval pi to 4. So it can't be there. That gives us a contradiction. So well, it gives us a set which is open in one topology but not in the other. So the topologies are different. Okay.